Welcome everybody to week 12. We're back from our break. Get started OpenSees in STKO is a series of classes that we started in April, I think. We have a 30 minutes presentations from me, then a time for questions. And normally if there is some assignment, but anyway, there's always the possibility to go on our forum. Takes some time for the link to work. Anyway, you find in the presentation the links to our forum where you can go and just post a question and we will answer to you. We answer daily to the questions. So we have you have a lot of support from us in there. Today it's week 12. We're going to talk about linear elastic analysis. We already discussed a model with linear elastic analysis in week 3. And so we're going to just take the same model. And not to make it boring, because I mean, linear elastic analysis is quite an easy task, especially for STKO users. We're going to add onto it a few, let's say, topics, a few ways to model that make the whole process a bit easier or optimized. So I have for you a lot of scripts that you can use in the Python API to make a few automations in your modeling, and also make a few of the tasks that are normally done by other FEM software, like node combinations or envelope of results. And so, I mean, it's not going to be much of a presentation. I'm just going to go through what I will tell you, and then we're going to open STKO directly, because today is not a theory class, it's a practice class, as the color says. So we're going to start with the geometry. I'm going to just try to draw very fast with you the geometry of this model from scratch. I mean, we're not going to do it all because of course it takes more than half an hour, but I can tell you how to automate a few of the things and like some tips on how to obtain certain things, like for example, the introduction of bracing. If you are doing a still structure, then we're going to assign an interaction and maybe use selection sets, which are very easy to use. Then we can use a script to assign an offset to all the beams in a model. Let's say this is a very simple example because we use just 2 types of beams, but normally in RC structure or a steel structure, you have very many different types of physical properties, sections, or also materials if it's an existing building. So you may need to automate a few of the tasks that you are actually trying to perform. And instead of having to click on all of the things you created, you can use the Python API to make things faster and easier. We have a script to select all the assigned physical properties so that we don't assign element properties to something that we actually don't need. And then we have other easy scripts for the automatic assignment of mass and self-weight, and the addition of that mass and self-weight to a load pattern. Then I'm going to teach you how to create load cases in the analysis steps and create new virtual results from the Python API in the Postprocessor. What is a virtual result? We need just this one theory definition before we start with the practice. So results that are created and manipulated through the Python API and STKO, they're called virtual. That's because they're not stored in the database. So if you close your Postprocessor file, SPD file, and you do not save it, you will lose the created virtual result. And so they are virtual in the sense they're not actually real. They're not stored anywhere. They are created and called. They are created every time they're called in the Postprocessor. So they don't belong to a database. This is really important because maybe you go a long way trying to create a lot of combination of load cases, and then in the end you close the file and you lose them all. And maybe you did not save your script each time to create each combination. So it's advantages because you don't need any additional storage space for this kind of results. So you can create as many as you want and they will not load on your computer, but it could be costly in terms of computational capacity if you need to ask for them numerous times and they are calling many other results to be computed. So just be careful when you use them and keep this in mind. So let's go directly to STKO. Let's I can drop in the chat. Let me just stop my sharing and fastly drop in the chat the files for today so you guys can open them if you want. Yes, there should be all the files. So we have our model, example 16. If you were here in the past months, you know that this is exactly the same, mostly the same. It's a bit slender because I changed one small thing. The model of week 3. So we are in our preprocessor. And I just wanted to start by showing you how to create the geometry, but we have to start from scratch, let's say. So if I open another STKO, I want to start the same model from scratch. In the folder that I just share with you, there's a series of scripts that you guys can use to follow what we're doing today. First script is called geometry. So what I did with this script, let's maybe open it in another way that's easier to visualize. Yes, here we go. So what I did with the script was, you know, there is this package, Python package that we created called PyMPC to interact with STKO through the Python API. So we import all the functions and methods in this package. We clear the terminal. We call the document, the preprocessor document. Then we find, we set the ID to 0. And if there are other geometry, we set the ID to +1, the ID that it's there. We create a function to add new geometries, and we create a function to create a point. A point is created through the class fx OCC builder with the method make vertex. You just need to define coordinates for such vertex, and it will be created into geometry with the same exact, let's say, command that you can use from the top geometry in STKO just by clicking on point and drawing your point in the render view. So the same task can be performed through the Python API. This is just, maybe it's not the automation that everybody would do, but it's just an example to show you that let's say, make your operations faster, you can interact with the render view and the geometry through the Python API. So what I want to do is, for example, I know exactly the locations of my columns at the base. So I want to recreate the points from which to extrude the columns. So I had inputted here the length of the, let's say, the distance between the points. And if I create a small loop, let me just comment this out for a minute. If I create a small loop, I can iterate over a list of distances in the X and the Y direction and create points with X and Y coordinates and 0 zeta coordinates. So I just run this script. Something is not working. This is not the version of the script that I wanted to use. Oh yes, I know what's happening. Sorry. Yeah, I ran the script. Let's wait for. It's actually working, but it's super small, so you guys cannot see it. So let's try again. No, I don't know why this is not working for some reasons. Let's try the other file. Okay, so I don't know, maybe it was a scale problem. If you see here, I've created points for the locations in which I wanted to extrude my columns. So let's just work in this file so it's faster and better. If we don't, let's not make any mistakes. So we can move everything a little bit further. Create our geometry here where I just created my points with the script. So what you want to do when you're creating your geometries, first thing is extruding your columns from here to the top. You know that the first height is 4 meters. So you go over here and you create your column. So in this case, in this model, we want to create braces. So what I suggest you guys to do is, given that we want to use truss element for the braces, and we don't want for there to be transfer of forces in the center, we want this element to be separated between each other and work at truss elements. So only axial forces are transmitted to this kind of element. We need to use the command make wire, not the command merge. Otherwise, this node will be created in between. What I suggest you guys do so is to first create all the beam elements of your model, and then go on and create the faces that are representing the slabs. Just for you to remember, there's still all the points that I created under it. So we have double geometries. Now in this point, if we click, we have two vertices. The vertex that I created with the script, and a vertex that belongs to the extrusion that I created. This is because the STKO is a boundary representation geometry, works with a boundary representation geometry. So you don't have separate instances are not like joined when they're created in the same place, but they get duplicated. So let's say that now I created my first level. If I go on and assign the braces to the side here, what changes if I use the merge command? This point is created and I don't have a truss element anymore. So what I will do is I will use the make wire command. And this is very convenient because now, of course, the make wire did not merge everything, but now we can merge this wire with the rest of the lines inside of our structure, and we don't have the additional node that we don't want. And then just afterwards, I'll create the face that I want to use for my slab, and then go on and create the merged geometries. In this case, for example, we have a staircase here, so we go on and remove a face in this position. And like that, we go on and create all of our structure up by, in this case, we cannot copy paste all the story because, I mean, the next story is a bit smaller, so we would have to create a new one. And the easiest way to do it would be to copy the point, no, maybe move the points at the base. Let's use this one. Let's see if it works. No, it does not work. So we would have to, well, because we merged the point at the base, so we don't have them anymore. We would just like run the script again, create those points again, which is quite convenient. Because as you see, for example, right now I lost my reference, but I can actually create it again very fast. Reselect all, deselect all the geometry, move these points up. Whoops. Move these points up here, and then use them to extrude again our columns of 3 meters. So we go in the terminal and we type 3000. There you go. Same goes for the next floor. We want to create the lines for our edges. Yeah, I'm not gonna just do it all because it takes too much time. But what I wanted to show you is that you can also create one single story and then replicate it for the rest of the structure. It's quite intuitive. What is the difference in this model in respect to maybe others that you can create? You see that we have inserted this staircase here with the ramps. The ramps have faces to model them, and this is used in order to use the surface load to distribute the load to the edges, so we don't have to compute linear loads for each of the beams on the side of the ramps and on the side of each of the slabs. Anyway, what happens is that we have both let's say lines that represent beams, and then we have lines that do not represent beams. If we just turn this interaction off for a minute, you will see that we had to add some additional lines in order to subdivide the slabs and obtain quadrilateral elements for our mesh. We need to remember that to these lines, for example, here in the center or here in the center of the ramps, we are not actually going to assign any property. And we have actually a system for do that in a very easy way. So just going a bit like further very fast, I had here some additional scripts that you guys can use afterwards if you want. There's one for setting up your basic units if you want to input data in different units and then convert it automatically. Then I have a script to calculate material parameters. When you create elastic sections, you can compute automatically the values for G, and that you can do also like further on with other, just using Python as a calculator. And then we have another script to assign an offset to the sections. So as I said, this is a very easy model. I have only 2 types of beam. I already designed these properties. To add a physical property, you go here, you create a new property. You find a section, an elastic section for our linear elastic model, define the material properties, and then go on and assign one of the sections that are like developed here. Or you can also find, I use, for example, for the column, a user-defined section. So by defining here the size of my section and then assigning like this thickness to the web and the other elements of the section. So you can do this for any type of sections that you have in your model, and maybe you have a lot of them. Let's imagine that you want all of them to be aligned with the level of your floor. For example, in this case, we have 2 sections of different heights, and we want them to be aligned. So what you can do is go here and assign the offset, which is, of course, the same size of the height of your section divided by 2 with a minus. And these section offset are related, like this is related to the local axis of your elements. So here, for example, this element has 0 local axis towards up, and then you give them an offset that is in the minus direction, so towards the bottom of your model. To do this, you can use a script. So there's this part of the script, which is for rectangular sections or for any other type of sections. We go into the document, like before we call the preprocessor document. We call the physical properties that are already defined here and all the items of them, create a property object, X object. And if the property is called elastic, so this works only on elastic sections, but you can also introduce it for fiber sections or for other type of sections. We get the attribute section, so we go inside here and we get this attribute sections, and we go into the custom object. This is a custom object for the beam section editor. We cannot, unfortunately, call directly the height of our section, so we found a workaround. We're going to create a visual representation for the section, call the bounding box that's actually bounding this visual representation. If you guys go here, this is the visual representation of the section, and it hits like inserted into a bounding box. So we call this bounding box, we call the minimum and maximum points, which are, let's say, a point which is here and one which is here, is bounding the representation of the section. And so the coordinate of the minimum point are already in with minus, and we assign this value to the attribute section offset of the elastic section as a quantity scalar value, exactly as the offset we just extracted. Then we commit the changes and we will obtain this here. Let me show you guys how it works. Of course, I mean, this will work on these columns too, but we don't actually want it to, so we will have maybe to change it, or we can create a list of elements over which we want, yeah, we already have that. So we have a list of elements over which we want the script to iterate. Let me check. Yeah, so this has been assigned. And as you regenerate the view, or like just use the command, this one, regenerate the view, that was not copy pasted at the bottom. If you regenerate the view, then you will have the offset assigned to your section. So this is just a quick trick that you guys can use. So going forward, let's say, imagine that we have defined the elastic section for all of our beams and columns. We have defined an elastic material for our cables for the bracing, and a truss property for the bracing, defining a sulfurous section for the bracing. We define an integration scheme for all of these sections inside of a beam section property. So we're done with our physical property and we want to assign element properties. So just so you know, one way to do this is to select everything to which a physical property is assigned with this method that I'm showing, and then drag and drop the beam element that we want to assign there. Of course, this should be called beam. Of course, this is easy now because I only have 5 properties, but what if I had 100? So to do this, I can use this script called selection. This script is going to unselect everything in the scene. So if I have something selected, it will unselect it. It's going to iterate over all the geometries created. And if to those geometries a physical properties is assigned called beam section property, I actually edited this myself. So whenever you have another type of elements whose another type of property is assigned and you want to select it by iteration through the Python API, you can use, you can just edit the script. And you iterate with this for loop, and it's going to select all of these beams. So let's just run the script. As you can see, it selected all of the beams. These things are assigned. Do we have a question? I've heard someone. No. Okay. Let's go forward because we don't have so much time. Exactly. So this is what you are doing to select all of the elements to which a beam section property is assigned. We can iterate over it with a for loop and use this command. This is very useful in this case because, as I told you before, we have some beam elements, some edges to which we did not assign any physical property. So if we were to do something like this, for example, just I don't know, selecting all the edges of my project and just drag and drop this, it would be very wrong and we would like encounter some mistakes. So sometimes if we try to make things very fast, we can actually encounter mistakes afterwards. But if we use some scripts, it makes our life easier. What's next? So a very easy way to assign mass and self-weight is also by a script. Because now that we define physical properties for everything, and then we define element properties, of course, we have the truss elements, but in this case, they were all the same. So there was no need for a script. We would just do like this, and then drag and drop the correct element properties. We are now going into conditions. To go into conditions, we need to put boundary conditions and of course, loads and mass. So in this case, we have a fixity at the base assigned to the bottom nodes. Let me go into condition tab so you guys can see better what's there. Yes. Then we also fix some of the nodes that are floating in the stair because we know these nodes are not going to move. And actually we really don't care about these elements that are joining in this node because they don't have any element properties assigned, so they will not contribute to the overall stiffness of the structure. So we have this fixity at the base and on these floating nodes. Then we have fixities at the master nodes of the rigid diaphragm. Oh, I did not show you guys how to create a rigid diaphragm. So an easy way to do it is to create selection sets. We have a selection set for all of our constraint nodes, and we can have another one for our retained nodes. This sounds like a tedious task to do, because you see, okay, I can just select them while I'm doing the interaction. But there's going to be a lot of things that can erase your interaction. If you merge something wrong, if you explode your structure, if you need to change something. So it's not a good idea to just select things as you do the interaction. It's a good idea to have everything you need for your interaction in a selection set and select the things as you go on. I'm not going to do it again because we already have our interaction. Let's just remove this one. In fact, we already had one. So what we have as condition, going back as before, we need to fix our rigid diaphragm nodes in plane. And we need to actually assign the rigid diaphragm condition to the interaction we created. In the, it's rigid in the Z direction, so in the third direction. Then we can assign self-weight to the slab as surface load. We discussed this in week 3 already, so I'm not going to go through how the surface load works. But what we did not discuss, it was the self-weight of the beams and the columns, because in the model we had before, we did not care about it. It was just an example and we didn't put it in. But it's like most probably something that you want to actually add to your models. So because mass you need for doing an eigenvalue analysis or any dynamic analysis, and of course self-weight you need if you want to create load combination and do a gravity analysis. So as you can see, these loads have been created with a script, and because all of their names are, let's say, from a formatting that we created here. So you define the weight of a structure, you define the units for the gravity acceleration, you calculate the density, and then we have a script that is going to remove any conditions called edge mass, or let me just open it a bit further, or elastic load. Yes. Okay, we can actually run it again because there's no other ones. It's going to remove all of them, delete them, and then it's going to take the ID of the last condition and iterate over it again by selecting all the physical property that has a beam section property, extracting from those selections the section, the attribute of the section, and then computing the area. Like, you don't really have to compute it, you just go in here and you call, these are already computed value from the properties of your custom object. And from this area, you can calculate the mass and the weight for each of these beam section properties. Create a condition that assigns the mass and the weight. So an edge mass condition, as you see here, and an elastic load condition. And then define the information inside of the condition. So for example, we have the dimension. If we're gonna use, hi Alex, do you wanted to ask a question?
No, sorry.
Okay, no problem. So defining all the attributes that we open up in the editor. So if we had to create this by ourselves, we would have to click here, edit, add, go into load, elastic beam uniform. We're gonna have to click here, say global direction, then assign the value here. And then select all of the beams to which this condition is assigned. We don't need to do this. And as you can just imagine, this is very, very useful if you have a lot of these beam section properties, a lot of these different sections in your model. So this is just a fast script that you guys can use, edit it, or if you want to create another type of condition, instead of LA load, I want to use an edge force. They kind of work the same, so it doesn't really matter. But if you really want to change and edit it to your needs, that's something that now you have and you can use. I'm not going to run this again because I will have to put them in the load pattern again, and we don't have that much time. Then after that, I provided you with a little other script, because of course, let's say you don't have to click here to add all of the conditions one by one because you have the script. But then when you create a load pattern, you would have to maybe imagine that you have 100 of these. You create a load pattern, you go here in elastic load, and then you go and select each one of these one by one by scrolling through them. And this can lead to many errors if you have a lot of those. So there's also a script here that if you want to add all the elastic loads to a specific pattern, you can use to create a load pattern with this. You just have to maybe create it before, creating the load pattern before, then select the ID here, and it will add all of the specified conditions to that load pattern. So actually today, this linear elastic analysis is very automated. So you have a lot of tools. Going forward, what is it that I wanted to show you next is how to define an analysis if you want to create load combinations. So apart from the self-weight, here we have live loads distributed over the slabs, and we have a wind load. Sorry, guys. We have a wind load, which is pushing our structure in the direction opposite to the bracing. So the positive Y direction on the side of the wind, and on the other side with a smaller rod here. So given that we applied this condition, we want to create load cases. This is not something that comes automatically in STKO, but you can build it. So you create your recorder, select the desired results. Here we did an eigenvalue, so we ask for the modes of vibration too. We ask for the local force to see the forces on the beams, section force, section deformation, reaction, displacement, and rotation. Okay. We add our constraint patterns. You don't need a script for this because it's very little, very little things. Here, we already discussed this. We created a dummy analysis to see the eigenvalue. We're just like building up onto something we already discussed in week 3. But then starting from here, we have new things. So we can add a load pattern with all of our self-weight and create an analysis to compute the self-weight. Now we have a linear elastic analysis, so we don't really have to care about, we could put linear here too, no problem. And we don't need a lot of time steps because we know this is gonna work. But then at the end, we wipe it. We wipe it and we remove the load pattern. We use the command remove load pattern that you find here. Remove the load pattern. You define the load pattern you want to remove, which has to be, of course, position in the analysis steps before this remove load pattern command. You reset the time, wipe the analysis, and start again. You create a new load pattern. Like here, you don't need a script because, of course, live loads is just on the slabs. You add this live loads and go on. You can just, of course, clone these elements because they will be always the same. We're going to run the same type of static elastic analysis on the structure. And you can do that for the wind too. So once you have defined your analysis steps like this, each of these analyses, LC1, load combination 1, load combination 2, load combination 3, is going to be a different model stage. Let's mesh and run our analysis. And see in the post-processor, I can extract the value from each of these model stage and combine them into load combinations results using factors and also into envelope results, envelope of combination. So we open the database just created. And as if you can see in the results here, you have numerous model stages. So model stage 1 is the one we defined initially for the eigenvalue analysis. Once we input the record here, this creates a model stage for the information up to this point. So in the first model stage, we have our modes of vibration results. So we plot them, we check everything works as expected, the model like is all connected and is moving together. This is something that I always suggest you guys do when you create a new model. First, run linear elastic analysis with eigenvalue analysis. This happens because these are local modes, no problems. We don't care about this. Of course, I save the information. Yeah, let's put this a bit less. Yeah, exactly. I save the information for these modes here. in a file called model, in which I have the period of my structure, and going down, I can see, for example, the model participation. No, it's not what I wanted to show you. Model participation mass, so that you guys can actually see which are the modes that are local and which are the modes that are global. Exactly, like model participation mass, exactly. Examples, you see the first two we saw, they have a lot of mass participating in its two direction and then very little. So these ones are not relevant. So going forward, in the next stage, we have the results for the self-weight. So we don't have modes of vibration here, we just have displacements. Exactly, gravity displacement. Of course, this is very big, very magnified. So we can open the script here too. Let us just put it on top of the editor and use our last two scripts for the day. Here too, we call, instead of the preprocessor document that we call here, the CIA document, we call the post document. Let's close something, because, yeah, the post document. We get a database that we added to our post-processor document. We define the load cases that we want to combine. In this case, we are going to combine the gravity load and the live load. So this is the result for the gravity load. This is the result for the live load. As you can see, the quantity of displacement is different. We're going to put some factors. Let's say we call this combination, I don't know, in Italian is stato limite ultimo, so SLU. And then we put factors to amplify the result for these two load cases. We can call specific results that we want to combine. So we can combine, for example, displacement, reaction force. You can see the names here and input them here as you want them. So we define some tags for each of these results. You can see the tags of any of the results that you want to combine already here. So yeah, you go in the surface color map and you see the tags of the type of results. And then if the result is nodal or elemental result, let's say corresponding to the names that we called here, we're going to have to give it an integer number to define if it's nodal or elemental. Then we're going to iterate over this counter in the range of the result name that we want to combine in the combination. Allocate a zero combined result to start with, and then process all the load cases that are there. If they are nodal results, we're going to get nodal results. If they are elemental results, we're going to get elemental results for the stage at the ED that we defined before, combining them by multiplying it for the factor that we defined initially here outside. They're gonna just like be counted in this initial counter. So this will work for the first stage and this will work for the second stage, of course, as in any for loop. And this combined result will be shown here in my database with the name that I define it, and just be added as a virtual result to my postprocessor file. So let's just run the script. As you can see, super fast, because the result is just virtual, it's not there. It's going to be called upon as we click on it. So we are in model stage 2, for example, and we're just going to call the combined result that we just created. So here you see, for example, in terms of section force, they combined actual load from both the gravity load with the factor of 1.3 and the live load with the factor of 1.2. What if we want to see combined result in terms of displacement? Here it is. So, of course, maybe there are some points with localized displacement, so maybe you don't see a better distribution. But if you set, for example, your range if I design a maximum of 0.025, I can see the distribution much better. So let's say we do this twice. We define another combination with just the live load and with just the gravity load and 0.5 of the live loads. And we call it in another way. We create this other combination results. And we go to our last script of the day to envelope these results into a different one. So we have to remember how we called our combinations, because of course I call them differently as in my example. And then assign, let's say, for example, we can envelope the maximum values from this combination and the minimum values from this combination. So we get another results in terms of, for example, of displacement here, but we could have called any of these other things. Just remember that you need to use a different function if you want elemental results. It's here, it's called get elemental results. So we get these results, we combine them, and then we set a new display name for another additional virtual results that will include these two envelopes. So say the process is the same, but instead of calling results which are not virtual, this one is calling results which are virtual. So clicking on here, we can show you, I can show you these guys in a new type of plot, which is normally maybe just more useful for this kind of things. So I'm going to, I know, yeah, but I actually plotted not elemental results, but nodal results. I cannot see in this plot. Let's change it for just for the sake of this example. Whip. And this we called like this section force. And we're gonna call them section force envelopes and probably give them different tags. We can copy these tags. Wait, sorry. These tags, these are not reactions for our result. Okay. Let's see if this works. Yay. So we go in our editor and we should find, yes, our envelope, for example, of moments given by both of the combination we described. As you can see, we have localization here for some reason. We should check why, to be honest. But yeah, so this is the kind of results that we want to obtain if we're doing an envelope. I have maximum envelope and minimum envelope. So for today, I think we're done for all the scripts that I prepared for you, and also let's say how to extract and see the results of linear elastic analysis. I'm sure you guys may have questions. I hope you guys have questions. Thank you and bye.